Now we will look at eigenspaces, the third of our eigen-whats. We've done this a few times during this term. We've taken words and added space to the end, and you can do this in life. Your friends may walk away, but then they weren't really friends anyway. We've had vector spaces, subspaces, and now eigenspaces. Now we've already seen eigenvalues and eigenvectors. This is just a bonus. The good news about eigenspaces is that I tricked you in the last slides and I showed you how to find eigenspaces without using the word. An eigenspace is the collective span of the eigenvectors of a matrix. So if you found the eigenvectors of a matrix and you create their span, which remember is the set of all possible linear combinations of them, you have created a subspace of Rn, where n matches the size of A. And that's the eigenspace of the matrix A. The eigenvectors, because you're forming this space out of their span, those eigenvectors are basis vectors for the vector space. So in those last slides, this was the example we saw, the 3x3 matrix A, eigenvalues of lambda equals 1 and lambda equals 5. 5 was repeated twice. Lambda equals 1 had one corresponding eigenvector. The repeated eigenvalue 5 had two eigenvectors with it. And so we could say that the span of these three eigenvectors is a subspace of R3 and in fact is the eigenspace of this matrix. Now it gets even better because within that full eigenspace of the matrix are subspaces corresponding to the spans of the individual vector or vectors as shown. Remember, lambda equals 1 gave a single eigenvector. The span of that vector is a one-dimensional subspace of R3. The span of the pair of eigenvectors that went with lambda equals 5 form a two-dimensional subspace of R3. And these are the eigenspaces of the matrix A. So if you are asked to produce eigenspaces, plural, of a matrix, just make the spans of the individual eigenvector or eigenvectors that came out during the search. So at this point, you can see and not freak out about a question that a couple of weeks ago would have looked awful. The question would be, find the basis vectors for the eigenspace of this matrix A. If you had seen that question a few weeks ago, you probably would have just dropped your stuff, turned around, and walked out of the class. All this means is find the eigenvectors of the matrix, because they are the basis vectors for the eigenspace of the matrix. So let's run through finding basis vectors for the eigenspace of this matrix, which is just finding the eigenvectors for this matrix exactly like we did in the last slides. But one more example never hurts. So here we go. The key to finding eigenvalues and eigenvectors comes out of this construction A minus lambda I, so it's good to see A minus lambda I, and here it is for this particular matrix. The determinant of this A minus lambda I will help us find the eigenvalues. Remember that they are where the determinant of A minus lambda I is 0. So here is the determinant of that, A minus lambda I, worked through and then factored, and so now we see that the determinant is 0 when lambda is 1, 2, or 3, and so this matrix has three distinct eigenvalues. When lambda is 1, we're going to go back and recover the matrix A minus lambda I with lambda equals 1 specifically in mind. So here inside the determinant bars is A minus lambda I. With lambda equals 1 in mind, then down the diagonal we will get negative 2, 3, and 2. And there we go. So this is A minus lambda I for lambda equals 1. Now what I'm not showing you here is what I did show you in the last slides. Just to speed this up a little bit, we're looking for where the matrix equation A minus lambda I times the unknown vector V is 0. The unknown vector V is the eigenvector we're looking for. The solution to that system is based solely on the row-reduced form of A minus lambda I. Here is the row-reduced form. And what we tell from this by row 3 is that V3 in the eigenvector will be a free parameter, and then V2 and V1 are both just equal to that V3, or that free parameter. So the solution set to that system of equations looks like this, which means a perfectly good eigenvector for this matrix when lambda is 1 is 1, 1, 1. Now, not going through that routine 2 more times, but you can try this. Hit pause if you want more practice finding eigenvectors. If we go through with lambda equals 2 and lambda equals 3, we will find these corresponding eigenvectors, 2, 3, 3, and 1, 3, 4. And what this means is that these eigenvectors are the basis vectors for the eigenspace of the original matrix A. And there you go. Everything you need to know about eigenspaces in just a few short minutes.